the linear velocities of the particles are different with respect to each other, related to moment of inertia between the two axes. So I equals Ig plus mr square perpendicular to the plane, which is z-axis in this case. And this is the expression for the kinetic energy of the rotating body. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. Continuing my discussion on the chapter System of Particles. In today's discussion, we will study two important theorems called the perpendicular axis theorem, the parallel axis theorem, and finally we shall derive an expression for rotational kinetic energy. Before going on to today's topics, we will just recapitulate, try to understand what we did in the previous session, where we defined a very important parameter called moment of inertia. And we told it is the resistance, opposition offered by a body to accept changes during rotational motion. Therefore, it was also called rotational inertia. And we mathematically measured it as the product of the mass of the body and the square of the distance from the axis of rotation. We defined something called torque. It is nothing but force acting on a rotating body. The word torque means force, but acting on a rotating body. And it is measured as the product of mass, or you say force into perpendicular distance. Its SI unit is Newton meter. And finally, we ended up understanding the law of conservation of angular momentum. Now today, first we study something called the perpendicular axis theorem, something related to moment of inertia, perpendicular axis theorem, very important, often asked in the exam for 3 marks. As the name itself goes, it is a theorem related to moment of inertia about some perpendicular axis. Now the statement of the theorem goes like this. The moment of inertia of a plane body. ಲ್ಯಾಮಿನಾ ಅಂತ ಕರಿತೀವಿ. ರೆಕ್ಟ್ಯಾಂಗ್ಯುಲಾರ್ plane bodies. Rectangular lamina. So the moment of inertia of a plane body perpendicular to its plane, is equal to the sum of the moment of inertia. Sum of the moment of inertia of the other two axes at right angles to each other and intersecting at a common point. A little bit absurd to understand the statement, but the meaning is very, very simple. It says, the moment of inertia of plane bodies, moment of inertia of plane lamina about an axis perpendicular to its plane should be equal to the sum of the moment of inertia of the other two axes acting at a common point. Very simple. There is no exaggerations here. So here I consider a plain rectangular body. I call this a plane lamina. And I construct a Cartesian coordinate system, a frame of reference, x, y, and z axis to the lamina. So this is the x axis, this is the y axis, and this is the z axis. Ix is the moment of inertia about this x-axis. Iy is the moment of inertia about the y-axis, and I is the moment of inertia about the z-axis. Ix, moment of inertia along the x-axis. Iy, moment of inertia along y-axis. I, moment of inertia along z-axis. So the theory says, now this z-axis is perpendicular to the plane of the lamina. So the moment of inertia about an axis perpendicular to its plane, that is I, should be equal to the sum of the moment of inertia of the other two axes, Ix and Iy, which are at right angles to each other, which act at a common point. Therefore, very clearly perpendicular axis theorem says I should be equal to Ix plus Iy. What is I? Moment of inertia about an axis perpendicular to the plane, which is z-axis in this case. Ix, moment of inertia along x-axis. Iy, moment of inertia along y-axis. X and y-axis are perpendicular to each other. They act at a common point O. Therefore, I equals Ix plus Iy. See, so simple. Moment of inertia about an axis perpendicular to the plane, as in the diagram z-axis, should always be equal to the sum of the moment of inertia of the other two axes. And what are the characteristics of the other two axes? They should be at right angles to each other, and they should act at a common point. They should intersect at a common point. So we say I equals Ix plus Iy. And this is called the perpendicular axis theorem. The same way, the next one, parallel axis theorem. Again, a very important 3-mark question. Parallel axis theorem. If perpendicular axis odidralva, ade reeti, this is parallel axis theorem, which says moment of inertia of a body about any axis. Moment of inertia of a body about any axis. No specification here. About any axis is equal to the sum of moment of inertia about a parallel axis. Moment of inertia about a parallel axis and the product of its mass and square of the distance between the two axes. Again, triggering out the statement a bit absurd here. Moment of inertia of a body about any axis should be equal to the sum of moment of inertia about a parallel axis and the product of mass and the square of the distance about the two axes, which means I is the moment of inertia about this axis. To find this moment of inertia, I will construct a parallel axis whose moment of inertia is Ig. Therefore, I becomes equal to Ig, which is the moment of inertia about a parallel axis plus the mass of the body and square of the distance between the two axes. So I equals Ig plus mr square. This is parallel axis theorem. Moment of inertia about any axis should be equal to the sum of moment of inertia about a parallel axis Ig plus mass of the body into square of the distance between the two axes, and this is what we call as the parallel axis theorem. So, dear students, we have learnt the two theorems, the perpendicular axis theorem and the parallel axis theorem, which will actually help us to calculate moment of inertia about a given axis. Now, going to something called as rotational kinetic energy. All of us know that the kinetic energy of a body which is exhibiting straight line motion is half mv square. Now I consider a rigid body. Now this is not linear motion. It is rotating about a fixed axis. It is a rotating body. Rotating about a fixed axis with a uniform angular velocity omega. So the body rotates with a uniform angular velocity, which means all the particles rotate with the same angular velocity. Here you should understand the linear velocities of the particles are different with respect to each other, but their angular velocities should be same. Therefore, I say the body is rotating with uniform angular velocities. So it has a number of particles of mass m1, m2 and m3 at distances r1, r2 and r3 from the axis of rotation, and v1, v2 and v3 are their linear velocities. Now we know that v equals r omega. Linear velocity v is equal to r omega. So, the kinetic energy of the rotating body or the first particle is half m1 r square 1 omega square. Second body, half m2 r2 square omega, or summating that we have E equals half I omega square, where I am summating from I is equal to 0 to infinity. And this is the expression for the kinetic energy of the rotating body. So, students, in today's session, we learned a very important theorem. First, perpendicular axis theorem. Moment of inertia of any body about an axis perpendicular to the plane should be equal to what? Sum of moment of inertia of the other two axes at right angles to each other and intersecting at the common point. I is Ix plus Iy, parallel axis theorem. Moment of inertia of any body about any axis should be equal to the sum of moment of inertia about a parallel axis and product of mass and the square of the distance. And now we studied kinetic energy of the rotating body. In my next session, I'll come up with the numericals on this chapter. Until then, go through the sessions, know the concepts, know the formulas. Only then solving numericals will become easy. Until then, have a nice time. Thank you.